Okay, so welcome back everyone. Today we are going to move from our sequence model predicting the next word, to sequence models to talking about attention, and then we'll talk about transformers. So the first thing is we just last time we just did a simple um, next word predictor, right? So we did that with the LSTM, which you will see here. Um, yeah, we did a simple, well, this was a LSTM classifier, but we did a next word predictor, right? But the same principle, the only difference is that we added word embedding, an embedding model. I think I can show us that. And let me bring this up. So we did a next word classifier, and it took a bit of time. It actually took 2 sessions, right? But I think it was worth it. Um, it was worth it. Um, yeah, I will leave the second bit, which is a sentiment classification, as an exercise. So we're actually going to learn how to basically the same principle as what you have seen here, where we will take words, take a vocabulary, um, convert those words to embeddings, right? Based on the vocabulary, and then create an embedding matrix. And then that embedding matrix, you can then use it to create um an embedding layer, right? Which you put into your model, right? And then we saw how to do the loading of the words, right? Using a word data set. And then we created a function to do collation, because one of the things is when you're doing sequence models, you have variable length input, but you can only put fixed length input into any of the models. So we had to do padding. Okay, so we use collate function to pad, and then the data loader, we make the data loader by pulling from a dataset class. The dataset class was just basically built around a token, so it will take all the sentences, tokenize the sentences, and then split tokenize that splitting sentences, and then find the IDs in the dictionary for those sentences, and then those IDs are now mapped to the actual words. So we'll now use the embedding matrix to pull the correct embeddings based on the IDs. And that's what the embedding layer does. So what you do is you are actually passing a vector of IDs, right, in the embedding matrix for each word. Then the embedding layer, which you can either create from a pre-trained model like this one, right? Using an existing embedding matrix, or you can even just create a random embedding matrix. Either way, it will learn. And then that embedding matrix will take a vector of indexes or indices. So for each sentence, instead of having the tokenized words, each word will now be represented by the position of that word in the um, vocabulary, right? And then the vocabulary is what constitutes your embedding matrix. And so the embedding layer is going to basically take that, convert those to actual embeddings, which are vectors that represent each word instead of a single index. And those vectors will now be passed into your long short-term memory, LSTM, or any other sequence model. You can try out this with a GRU, right? GRU will give you a similar kind of performance, but it'll be faster to train, right? And then all of that, the output from that, you're going to take it into a fully connected layer, right? And that forms your forward. So you do the embedding, you do LSTM, you take the output, but you take the last output. By the way, there are different ways, different variations of this. You could also decide, rather than taking the last output, you could decide to um, take the entire output, and then, you now have to make your fully connected able to take the entire output rather than just the last token. Sorry, the last output from your sequence, the last timestamp, basically, the last in the sequence, but you can take the entire everything in the sequence and put. So there are different ways you can do this, right? This is just one of the ways of which output do you put? Now, I did not do a graphical, intuitive representation of this, but and then the training loop is standard training loop. The only difference here is that we now have the data set, the data loader. So you're not training on the entire data set all at once, but you are loading in batches. And you can see that the batch size, when we created the data loader, we specify a batch size here, batch size of 4. And we also mentioned that it should shuffle. Okay. And we use that to train. So we train in batches. This is just an example of if you are training on a large amount of data, millions and millions of you know, data, um, data points or rows, you cannot load all of them at once into your memory. So you use batching. But if you were just training on a few sentences like what we showed here, we really didn't need to do that. Or we could just make the batch size to match the entire size of the data set. But be that as it may, this is just to show you how you can use PyTorch data loaders. And then that's it. We now made a convenience function here to help us predict. So instead of having to deal with numbers, which is what is actually happening inside the model, we allow it to accept the text, right? The entire sequence of text, the indexes, right? The word to index and the index to word. And what this predict next will do is it will actually give you the next word. So with this helper convenience function, I don't need to have to remember indexes or anything. I just type in the words and it's going to give me the next prediction. And that was it, right? So this is basically how you train what we call teacher forcing. And we're going to talk about teacher forcing shortly when we talk about how you are training large language models, right? Or auto-generative models. So basically, teacher forcing is where you are forcing the model to learn based on sequence of text that you provide. And the next word in that sequence that it is to predict, you also provide, right? Rather than it generating it, right? Which would be auto-generative, okay, if it was the one generating. But this auto-regression forcing, and it learns to predict the next word. Here it wasn't really okay because basically it was a very small vocabulary. There's something I had wanted to do here to an improvement. Okay, so here there's one other thing I tried to explain here, which it was in the last recording. This is basically the basis for GPT, for generative models. In fact, not just GPT, generative, language models. Essentially, you train it to predict the next word. Then when it predicts the next word, you take that next word and you append it. So what I did here was a loop, right? A simple loop, okay? And in this simple loop, um, we basically just say, okay, predict the next word. When it predicts the next word, I take that next word and I append it to the original prompt, which started off with something like this. And then I now use that new updated prompt that contains a previous prompt plus what it has predicted. You use that as a new prompt and you loop again and you plug that back in and ask it to predict the next word after that. So it will keep on doing that predicting, and that's essentially what generative language models are. And you could see that it did this, right? It quite did like an LLM. The only thing is that it keeps repeating stuff here because I had very limited vocabulary, only a few sentences, right? So look at all the sentences. It cannot come up with words that are outside of this vocabulary because I didn't train it on anything outside that. So because I had this limited vocabulary of just 20 words, right? It really couldn't come up with anything else. It basically overfit on this anyway, right? So the next step would have been, okay, yeah, so the thing is this model is learning memorization because it is the parameters are so much, but the amount of data is so small. So it's basically memorizing things. But you can try any of these databases, right? That contains a lot more words, right? IMDb, for example, Wikitext, right? Tiny Shakespeare. And then you will start seeing when you train on this kind of database that has a lot of words, right? It will now yeah, let's look at IMDb. You'll see that yes, it's basically a database of well, this is not what I was looking for, so I need to go back. Not the database itself, but the not the site, but yeah, so I will look for this maybe on Kaggle or somewhere. And I'm also going to do a demo, right? That will, yeah, so there it is. So you have this IMDb data set on Kaggle, right? So now imagine if we plugged this data set. I probably can just do that now, but I don't want to spend too much time on this because there's so much for us to cover today. But imagine if you were to take this data set that has so many words, right? It's a data set of 50,000 movie reviews, right? So just take this, right, and plug it back in here. We tweak it a little bit. So instead of using sentences as we have here, right, we can just load this entire IMDb data set, and it basically works the same way. As a matter of fact, I feel like, okay, maybe I can do this. Let me see. Let me make a copy. Um, yeah, let me make a copy. Uh, so imagine if we could do that, right? I'm not going to spend too much time on this because I don't really have a lot of time, but let's see what we can do with this. So here we import Torch. Need to also import Cargo Hub as KH so that I can load. So so now yeah, so IMDb. Okay, so I can just load this. Let's see. Um, by the way, this is not what we're supposed to do today, but okay. So I'm going to go look for code that I can easily use. KH dot download data set. Yes. I need a reference because I can't remember exactly. Fortunately, I don't memorize a lot of things these days. Um, when was the last time we downloaded stuff from Cargo? Okay. All right. So yes. Um, so this says download data set, but this says data set download, and then we post the link. But I don't need to post the entire thing. I just start from here. So yeah, this will download it for me, and then data frame. Well, it doesn't need to be a data frame because I don't know if it's CSV, but let's just see if it's a CSV, and we can extract. So I assume the it is. I also need pandas. Okay, so so this is the data set, and if I go check the data set, it says it has one file, and that file is called IMDb dataset. So this is the name of the file that we will use if we want to do that. And I think this was properly guessed, so this is okay. And I think it's a CSV as well. So yeah, it's downloading it. Right. So this is, yeah, this is even good because here you can use this for sentiment analysis as well, right? But here, I don't even want to use it for sentiment analysis. So I'm not going to take the sentiment part of it. Rather, I will now use it to generate the sentences list, which is basically a list of everything um, in the review, and it has a bit of HTML as well. But yeah, we'll let the model learn that, right? Um, so to get sentences, we will just pull that column and get it as a list, right? So Yeah, so that's basically it. We pull it, the review column, we get it as a list. So you now see we have this, and that's it, right? So we have all the sentences. Everything else will just fly because this was made to be very generic, right? That's one good thing with writing code in a way that is generic, right? So now I now have a lot more sentences because I pulled IMDb. I'm not going to use the sentiment. This is for sentiment analysis or sentiment classification, which could be the next task to do, right? And then let's run this. Everything else will run. I just click on run all, and it's going to do a lot of stuff. We'll come back to this, but what this basically tells you, yeah, so you can see we have a lot more words here, a lot more words, a lot more words, a lot more words, a lot more words. It's a lot. Yeah. So collapse this. Uh yeah, what to VEC has done, the embeddings. Um we'll build a next word data set. Um and it's still building the data set. Um I probably shouldn't try to print all the samples. That's what's taking so long. Um, yeah, but I'll let this run. When it's all done, we'll train the model and then we will see how well our IMDb, the model we train on IMDb, how well it is able to speak or generate words. So I'll let this run and we'll come back to it. So anyway, that's what we did, right? This is prediction of word sequence. Now, or the next word in a sequence. But there's what we call sequence to sequence model, right? So in a sequence to sequence model, what you are doing basically is you are the input is a sequence and the output is a sequence, right? When you do next word prediction, the input is a sequence, but the output is a probability distribution of what is the likelihood that this is a next word, right? That's a next word prediction. For classification, for example, sentiment classification, um, what you have is um, the input is a sequence, right? And the output is, um, well, it could still be a probability distribution, which is still what it is, right? Classifying what is the likelihood of, whether it is likely a happy or sad or whatever. So it's still a probability distribution. So in both cases, it's probability distribution. But when you are doing a sequence to sequence model, what you are passing in is a sequence and the output is another sequence. So a good example of sequence model is you are training a language translator. So you are giving it um, in one language, right? You're giving a sequence in one language, maybe in English, and then you're asking it to generate to you um, the equivalent of that same sequence in another language. That's sequence to sequence model. So it's kind of different, right? The way you train such models, and the way the architecture is, right? You're actually going to chain two things. You have encoder and decoder. The encoder is the one that takes the input and is able to convert from one sequence, right, into a context, which is like the internal meaning of that sequence, whatever that word or that sequence of words is. Then the decoder will take the internal meaning, right, and then decode it into the other corresponding sequence, maybe the same thing that was said, the same input, but in another language. So that's a good example. And you can see here, so things like translation, language translation. The other place where you could use this kind of sequence to sequence model would be if you are doing something like speech, um, you know, speech recognition. So the input sequence is a stream of binary a binary stream, let me put it that way, right? That represents the sound that comes in. It basically bits and bytes that directly represent the waveform or the sound that comes in. That's the input sequence. And then you still training on that sequence, and the output is the actual words that correspond to that. Okay. So that is that's basically how sequence to sequence models work. Now, typically, if you are doing sequence to sequence models, then it means that um, you have to have both sequences, right? You have to have both the input sequence, right, and the output sequence, right? Now, and they could have different lengths. They could have different lengths. It's not like it is going to be the same length. As you can see, the length of the English string here, right, is shorter than the French string, and so on. Okay, so that's the thing with sequence to sequence, um, models. So the encoder compresses. So the way it works using the standard LSTM approach is that the encoder will first of all compress the input sequence into an internal context vector. An internal context, that context vector basically represents the meaning, right? It represents the meaning. Now, that context vector could have a short, um, it typically is short. It might even be shorter. Well, most times it's even shorter than sequence because you're essentially compressing it, right? But um, one of the challenges, and we'll talk about the challenges of using sequence models, right, which gave rise to this whole transformer architecture, right? Um, when you have that context vector, the decoder is now able to take that context vector and then it knows how to extract and basically generate the output. Okay. So this is how the early translation systems used to work. I talked about teacher forcing here, where when you're training a sequence to sequence model, just like what we did now, we were training it to predict just the next word. But when you are doing a sequence to sequence model, you are going to put in the encoder and then you are going to put in the decoder. Then the decoder has output. Then when you are training it, the decoder is actually predicting only one token at a time, just as the encoder is consuming one token at a time. So the issue is that sometimes the mistakes will compound quickly, right? Um, but you can use teacher forcing. Teacher forcing is where you are giving the model both the input sequence and the output sequence it's supposed as a training data. The output sequence it is supposed to generate. So when you give it those, then of course it is forced to try to predict that. So that is teacher forcing. And that's it. Instead of feeding the model's prediction, you feed the correct token during the training, right? The downside of teacher forcing, the benefit of teacher forcing is that you have faster convergence and you have more stable training. But the downside of teacher forcing is that um, you sometimes may have a training inference mismatch, right? And the model becomes reliant on the history having to be correct. So those are some of the challenges. So, and that's it, right? Now, in order to yeah, so this is example code for sequence to sequence. You can see a simple implementation of encoder and decoder. Now you see that the encoder is an LSTM, right? Encoder is an LSTM and just a single LSTM with the input size and the hidden, and batch first is true. And then when you are doing forward, you take the X, which is the incoming sequence, right? And you take that incoming sequence and that goes into the LSTM, right? And then you now look at the hidden state and the cell state, and you are returning the hidden state and the cell state from the encoder, right? And of course, the reason for this is because um, the decoder will also need the hidden state and the cell state. The cell state is what we call the context, or well, you could also call the hidden state context. But in this case, right, the cell state, that's what we refer to as the context vector. So it's actually a vector. And this is what the decoder will use. So in the decoder, you can also see that the decoder is also made up of an LSTM as well, right? So that's why it's called a sequence model, because you have an encoder which is a sequence model, and then you have a decoder which is a sequence model. And in this one, again, it's the same thing. You have an output size, you have the hidden size, batch first, but the decoder also has a linear layer, which is what helps you to predict. So remember, whenever you're trying to do prediction of anything, you always add a linear layer to the LSTM, right? So the forward path of that is it will take the input that you give to it, a single token, then you also take the hidden and cell state. So this hidden and cell state will come from the encoder. And then you give it an input, and it's going to do a prediction of output, right? And this is also hidden and cell state, but we don't need this. So we take this output, which is also a sequence of the same length, right? As what you have defined as the output size, and you just send the output out. So it's going to give you a sequence, not a single output prediction, but a sequence, right? And that's sequence to sequence model. So now sequence to sequence models, before we had transformers, is what was used mostly for this whole thing about language translation, speech to text, even text to speech, all of a whole bunch of stuff, right? Because that was like the best architectures at that time, right? And yeah, it was great, right? But yeah, so this is kind of summary of what I'm saying, right? It maps an input sequence, right, to you know, an output, variable length output sequence using encoder decoder framework. So I've shown you how the encoder and decoder is. And they were used for language translation, summarizing text. So the summarizing text is another good example. You train it on a large body of text, and then the output will be the summarized version of that text. So that's what you use as training data, as the training the Y or the true label data, if I may use that terminology, right? So and a whole bunch of stuff, right? So what they just do, like I've said, they compress the input into a context vector, and then that is decoded by a decoder into the output. So the two main parts, the encoder, which processes the input sequence, which could be anything, words, time series, compresses into a context vector or hidden state. That context vector, that's the cell state or hidden state, depending on what you are using. If you're using a LSTM, you have both cell state and hidden state. If you're using a GRU, you only have a hidden state. If you're using a RNN, you only have a hidden state, right? So that cell and hidden state will now be passed into the decoder, right? That's a context vector. And then um, you also give it X, which is the previous things it has already predicted. Okay. And then it can now generate the output sequence, and it's typically one element at a time. So sequence models can handle variable length inputs and outputs, because you can see sequence models are meant to handle variable length. For now, we use pad, right, to pad the differences in length between the multiple different, um, elements in a batch. But there are other ways you could do it, including compression and marking where each sequence ends and things like that, right? So you can see that in the past, we were using RNNs, recurrent neural networks, long short-term memory, LSTMs, gate recurrent unit, GRUs, you know, to make these sequence models. But they were not really very good. In fact, in between, two real techniques came up to improve. And we'll talk about some of the challenges that they had. But I think one of the biggest challenges of sequence models was the vanishing gradient and exploding gradient. It's still there. And it's worse now because you now have two sequences, right? So, and those were the challenges. So a lot of different approaches were invented, were, identified. Researchers came up with a lot of different ways to tackle some of those. Training techniques that came up, we already talked about teacher forcing, right? Where you keep feeding both the input and the output with the ground truth, the real data, and you speed up convergence with that before you start asking it to make its own predictions. But then a new concept came up, which we call the attention mechanism, right? So the basis, I'll talk about attention mechanism separately, so I'm not going to dwell too much on it. But the basis of attention mechanism is the fact that the meaning of a word actually depends on the words around it. That's one, that's what context means. A word is in a particular context. Its meaning changes based on the context, right? It may not be exactly the same. But attention goes on to say that even in that context, it is not every word in the context. That is what I mean by context now. All the words that surround the single word that you want to identify its meaning, right? It's not all the words around it that matter to its meaning. There are some words that don't matter. There are some words that matter, right? So the words that greatly affect the meaning of another word, right? Those are the words that we say they attend to it. So the whole attention mechanism was an identification of that fact, the fact that it is not every word that has equal effect on the meaning of a single word, It's not all the words in a context, right? But it's only a few. And the attention mechanism was a way to train networks to identify which words. And so when those words occur, they will change the meaning of the word that we are trying to either translate or find its meaning in a more impactful way. So this allows the model to learn to focus on specific parts of the input during decoding, right? Those parts of the input, basically which words, if you're talking about language or sentences. But if it's other kinds of input like, speech, sound, and so on, they may not be words, but whatever the smallest unit of those things are. So anyway, we'll talk about attention later on, but those were two big things. So at the end of the day, you see that you have the encoder and decoder architecture, right? Um, yeah, I think I've mentioned this already. Some of the common use cases, machine translation, which is converting English to French or English to Spanish. Mentioned already, chatbot and question answering. So question answering is pretty interesting, right? You can give a bunch of questions and then you train it on a bunch of answers, okay? And you can give it, this leads to that conversational response that we're talking about. And this is how chatbots were done in the past before transformers came. Okay, you were training basically sequence models. Then image captioning. So you can give the image is a stream of um, pixels like we have seen, right? And then you train it on a bunch of words. So, but the thing is that for the image captioning, you would need to pass the image through an image model first, like a CNN, a convolutional neural network. And then you can then take that image and, you can stack the outputs of it maybe in some form, or just pass the image as a context, maybe the last stage, the filter or whatever, what comes out of the filter, and you pass it into that will be the encoder. You pass it into the decoder and use that to generate captioning, time series prediction, and so on, right? But one key thing, so you can see here, you have embedding, where you embed all the words, and this is the encoder. This is still an LSTM. So you can still see this is this the rolled out, the unrolled version of the LSTM. It doesn't mean that yeah, this is each time step. So you do embedding, you pass it in, and then that output, which this output is the hidden state or cell state, basically context, now goes into the decoder, right? And the decoder takes two inputs, the cell state and the word that was there before. in other words, what it has already generated as its output. If it hasn't generated anything, it starts with a go token, which says, okay, you haven't generated anything, just start, right? And then it generates the first word, I, in this case. And then that first word is used as the next input in the sequence. And the state from this is also used to give the input. So it generates the next word. And this next word again is used as the input. So each time the previous word that was generated is what we will use as the input, the X, right? Uh-huh. So that's so but one of the challenges, right, that you see with this sequence models, the way it was days, was that you are taking the sequence to sequence pipeline. The encoder is compressing the input sequence into a context vector. And this context vector can be very small, right? And then that context vector is now fed to the decoder, and the decoder will now generate the output sequence. Okay. So imagine compressing an entire sequence into just one vector. That vector can be really small. Well, you could make it bigger, right? But so it's a problem because think about a 500 word article and you're compressing into one vector, and that one vector basically just think of it as if a single sentence. You are taking a 500 word article, you compress it into one sentence, right? Then you now take that sentence, and that's what you use to translate into another language. You now know that you've lost a lot of information. There's no way you can compress a 500 words into one sentence without losing a lot of information. And that was the biggest challenge with the way sequence to sequence models were done, right? A lot of information loss. Once the sequence started getting really big and you could not compress without loss into this context vector, okay? So you now find that as the sequence grows longer and longer, the performance of the entire model drops because you lose information. And so the decoder is not going to really do a good job. It's not going to do a faithful job. So you find that the early translation systems, this is what was used for language translation in those days. They will start struggling when you give it long sentences. Of course, long sentences, that means the sequence becomes very long. You lose a lot of information compressing it into the small context vector, right? And same thing, paragraphs, technical text that contain a lot of technical information that they themselves are, in a context, right? And then you compress it. So the main problem, right, with this approach to sequence models was that the decoder could not also selectively choose earlier tokens. It could not decide which tokens matter, right? Um, First of all, because the earlier tokens that come from the encoder are all compressed into context. Then secondly, because its own tokens, earlier tokens that it is generating, yeah, it's generating one at a time. So it only knows the last token that comes in. If you look at this architecture, right? It doesn't know like this, at this time step, right? When it's predicting good, it knows arm, but it also knows the state, but it doesn't know what was before arm. Of course, normally the state would represent what was before arm. But remember, this state comes from this context and it's already compressed. So you lost a lot of information there. So yeah, so everything must fit into a fixed size representation. So the issue was that the decoder needed a way that it could dynamically access information to basically learn which of these earlier tokens matter most in generating the next token. This was key. And that is when this whole idea of attention mechanism, people started thinking about it and developing it, right? And the idea behind attention mechanism is that the decoder doesn't need to remember every single input, right? In generating its output, right? The decoder only needs to look back at all the encoder outputs, right? But it only needs to select what matters, okay? So a good example of what attention is, and we're going to look at this in more detail, is that when you are translating something like the animal didn't cross the street because it was too tired, let's zoom in on this it, right? What does it refer to, right? For a human being, you will know from context, oh, it is actually referring to the animal, but it could also be referring to the street, okay? Is it the street that was too tired, or is it the animal? It refers to what? This is some of the challenges that language models in those days were facing, right? The meanings like this, especially if very long sentence. You know, if the sentence is short, you can actually figure out that it refers to the animal. But in a very long sentence, it may lose all of this context because of that compression that we talked about. So it will not be able to figure out what was it referring to. And this is why we're having so many challenges with language translation. So now, what the attention mechanism now allows sequence models to do, especially for the decoder side of it, is that you compare the current decoder state with all the encoder states, all previous encoder states, right? And then you compute what we call an importance score. We'll talk about that shortly. And then we take a weighted sum. So what is importance score? The importance score is saying for this current state, which you can say, okay, for this current um, output that I'm trying to generate, it, for example, what is the importance of because when it comes to this it? What's the importance of street when it comes to it? What is the importance of the? What's the importance of cross? So each of the words that came before it calculates the importance of each of these words to the meaning of it, and therefore to what should come after it. Okay? So when you do this, then you can take a weighted sum, right? And that gives us this attention. We're going to talk about attention in detail, QKV. What is QKV? And softmax. We already know what softmax is. Softmax is basically a way to take a distribution, right? Remember, this is going to give you a probability distribution. You take that distribution and you make it so that the sum of the all of them will be one. That's what softmax does. Softmax means any set of numbers that you put into the softmax, it will rescale all of them. Think of it like a standard scaler, but it's not scaling based on um, the mean and standard deviation, right? It's scaling on the fact that all of them should add to one, but still maintain the relative magnitude. So the ones that are really large will still remain large, and the ones that were really low will also still remain low, right? So at the end of the day, if you want to pick the highest probability, it's still the one that has the highest value in the non-softmax version, which we call the logit. Okay, so this importance score that we're talking about is actually a dot product between Q and K. Q is what we call the query, and K is what we call the key. And we're going to talk about what those mean. This is a dot product, so that's why I have to transpose it, right? And then it's a weighted sum, so we divide it by square of dk. Dk is the basically a measure of the depth, right, of the attention. Um, Basically, it's a scaling factor. Let me put it. We'll talk about it in detail. And then when you do that, you do a softmax, right? So this softmax is, remember, is a probability distribution that all of the elements add up to one. You now take that and multiply by V, which is another matrix of values that represents, okay, this is actually what the value should be. We'll talk about that in detail. So attention was a big breakthrough, mainly because attention allowed the decoder to access the entire sequence, not just the compressed vector. So if you go back to this, what attention did was this context vector was removed and thrown away. So we don't need to compress, the encoder doesn't need to compress into a context vector and then send context vector to decoder. Rather, encoder now connects direct to the decoder. The encoder does not send a context vector to the decoder. It sends the entire sequence that it has so far been trained on, right? And then the decoder can then, well, okay, it actually sends the key. right? We'll talk about that. It sends the key and the query, right? And then the decoder receives that, and then it uses the key and the query, and then the value to calculate what the values, what its output should be, basically. We're going to look at that in detail. So the decoder was able to access the entire sequence instead of just a compressed vector. And that gave a lot of benefits because it means that the decoder could handle longer sequences. Since we are no more compressing the entire sequence into just a single context vector, which would limit, basically, it's a lossy transfer of information to the decoder. The decoder is now able to see the entire sequence that comes from the encoder, so it gets all the information. But more than that, the decoder is also able to learn the relationship between the different elements of the sequence. So in this case, the relationship between different words, which word has most impact on the other word, and so on. So that improved the translation quality. And the most interesting thing is that the attention was what led to being able to parallelize training in the transformer architecture. So take note that attention is not the transformer architecture, but attention was used in the transformer architecture to make it, it became really powerful in transformer architecture. The interesting thing is that you can still use attention in LSTM-based sequence models, right? And I'll show examples of that, but not in today's class. Today I want to just focus on attention and then transformers. Because kind of transformers have overtaken LSTMs and so on, RNNs in language translation and all of those long sequence kind of problems that require encoder, decoder, and all of that. But there are still a bunch of problems which we'll talk about, which the LSTMs, the GRU, the RNN will still do it better than transformers. So it's not that everything has to be done with transformers. That's one thing you need to know. So transformers is a paper that Google, a team of machine learning specialists and experts, researchers at Google, they did a lot of research and they wrote this paper in 2017. And that paper is called Attention is All You Need. I can send you a link. You can even Google everywhere. It basically, they outline the entire architecture of transformers. And why they call the attention is all you need is because prior to that paper, people always felt that you cannot use attention on its own. You have to take encoder LSTM, then put attention in between, and then you have a decoder LSTM, right? So there was always this feeling that, okay, attention improves encoder, decoder, information transfer. So attention allows decoder to access data better or sequence, the encoder better. But these guys came to prove that with attention, you don't even need the LSTM encoder or the LSTM decoder anymore. You don't even need LSTMs. You don't even need recurrent neural networks anymore. You don't even need sequence models anymore. With attention, that's all you need. That's why they named their paper Attention is All You Need, because you did not need LSTMs or GRU or any kind of sequence model anymore. Just using attention and the architecture of attention was all that was needed. So they named their paper Attention is All You Need. So, but one thing we need to understand is that transformers did not replace recurrent neural networks, right? They only solved a fundamental memory limitation, which is the limitation of the context vector, right? So they opened up a new vista of applications, which we are seeing today, right? But LSTMs and recurrent neural networks, GRUs, and so on, they still are very useful in another set of problems, which we'll talk about. Now, for transformers, so I've talked about transformers. Then we had these other architectures that basically followed transformers. So BERT is basically a transformer-based architecture, that was developed after this attention paper, right? Um, to basically it was a language model built by Google. So they basically used transformer to uh, build BERT. And the full meaning of BERT is actually bidirectional encoder representations from transformers or based on transformers. Okay. So, but they use only encoders. They didn't even use encoder decoder. Well, I'm not going to go into all those details, right? But BERT was one. And then we have the GPT, which a lot of us now know. A GPT is basically a generative pre-trained transformer. So you can see that the T in these two still refers to transformer. And you'll be asking yourself, what is a transformer? We'll talk about transformer shortly. And then the modern large language models, almost every large language model today is built from a GPT, which is a generative pre-trained transformer. And we'll talk about what that means. Okay. So the question now, like I said, it doesn't mean that because transformers came to overtake um, the traditional recurrent neural networks and sequence models that they have become obsolete and useless. There are still a class of models or problems rather that this RNN family of models will be much better at doing than transformers. Okay. So for example, when data is strongly temporal, because transformer has lost the sequential nature. That's one thing you know. Yes, the fact that it can solve sequence problems does not mean that it is sequential in nature. In fact, it is the very fact that transformer remove the sequentiality or sequentialness of it by removing the LSTM in the code encoder and the LSTM in the decoder is what made transformer become very fast for training and all of that, because LSTMs are really, if any sequence model is really slow to train, right? So the transformer is not inherently sequential, right? Unlike the RNNs. So any data that is strongly temporal, where there is a lot of um, correlation in terms of the time sequence, it's still better to use RNNs, right? For example, sensor streams, financial ticks, right? If you are doing any kind of financial prediction, whether it's stocks or crypto or whatever, right? Control systems and anomaly detection. So some of these are things we could look at, later on. Um, if you need low latency inference, transformers are very heavy. They take a lot of time for inference, but GRUs are extremely efficient. So there are some problems you say, okay, I want to use a GRU. If the data set is very small, you don't really need transformer because transformer require large scale training, okay, because of the size and complexity of the attention that's in a transformer. So if you have a small data set, a transformer is likely going to just overfit on it. So it's better for you to use standard sequence models, right? Um, the RNNs generalize better when you have low data regimes. Again, because transformers will tend to overfit. Then if you have edge deployment, so if you want to deploy your models on edge devices, like on phones, devices that have low compute capacity, low power, or run on batteries and so on, transformers can consume a lot of power, they require a lot of memory and so on. So it's better for you to use RNNs. It's better for embedded machine learning. So you now see that transformers didn't really come to replace RNNs. They just came to make RNNs were being used for language problems, and they were struggling for natural language processing problems, and they were struggling, right? So transformers basically came and took that over. But that's what most people used to see. When transformers came in and solved the problem, oh, it was like, oh, transformer replace everything. But transformers do not replace everything. They are now really good with language kinds of tasks, but the RNN still remain better in time series, simply because the RNN are still sequence models. They still have time steps, and they understand that concept of time. Transformers are not inherently sequential. They are still parallel. The only thing is that you can introduce sequentialness by several methods, which we will talk about. So this kind of gives us an idea of evolution, of the sequence models. You started with RNNs, okay? First memory-enabled neural networks that could think about past history and so on. But they had a problem of vanishing gradients. And then after that, we had LSTM GRU, which solved the long-term memory by eliminating or minimizing vanishing gradients. And they started enabling practical natural language processing. But then, since natural language processing was more of sequence models, we started having this context loss, information loss in the compressed context. So what happened was attention came in, removed that, allowed a direct mapping from decoder to encoder, and that increased accuracy for language tasks in particular. And then after attention, we just came to transformers. Transformers were basically, hey, we don't need any sequence model. All we need is attention, right? And then we have a few things around attention, basically um, a stack of, linear layers. That's all. And we're going to look at the architecture of transformers very soon. So a stack of linear layers around plus attention mechanism, and that's a transformer. But it allows for parallel computation because I don't need to bring in my sequence one at a time, one token at a time. That's the difference between transformer and standard sequence models. Standard sequence models, remember, when you see something like this in a sequence model, it doesn't mean that this is parallel, right? This is still a single model that takes a single input, but these are different time steps. So this is the step one, the first word, then the next word are, but it's still one at a time going in, and going out is one at a time. So it's still sequential and it's slow to train because you have to wait, for each, thing. So think about it like people are standing in a queue, 10 of them in a queue trying to go through a single narrow door. That is a sequence model, right? But transformers now made it possible that you can, that unrolled version of the sequence model, that's what a transformer is for real. It's not like if you see a transformer, it's not like it is how do I put it? It's not like it is a schematic or a way of representing it, right? That's actually what it's actually stretched out. All the inputs, all the tokens in the sequence go in all at once. So a transformer is now like, instead of having 10 people in a queue trying to go through one door, where each person represents a token to be trained, you now have 10 people in a queue, but all of them are going through 10 doors. Each of them is facing their own door and all going in at the same time. So you can see that it's times 10 the speed. So you could actually, transformers basically improves training speed by times whatever number of sequence length that you design into your transformer. So that is kind of the transition which I wanted to bring us to between the RNN and the transformer. So are there any questions before I move on to the class for today? Well, it's a continuation, right? We are now talking about the attention mechanism itself, right? And how it goes into the transformer. So we are going to talk about what is attention, what is a scale dot product attention, and what is the math around attention, right? And then we'll look at the transformer architecture and then other things around transformer architecture, including things like the positional encoding and then new modern improvements to attention mechanism. So we go. All right, so we've gone through this slide already, which is like, what was the problem with sequence-to-sequence models, the way it was done before? It was simply the issue that we compress all of the entire sequence into a single fixed length context vector, right? We've talked about that already. So if you are using encoder, decoder, recurrent neural networks, you have the input sentence, you compress it into one vector, which is a context vector, which is that cell state or hidden state or whatever. And then you send that to the decoder, right? So you lost a lot of information, and these were the problems: information bottleneck, long sentences, you lose the details at the beginning of sentence, long range dependency. You could not learn, like I said, the it, right? When you say it, did not cross the road. I can't remember that sentence exactly, but that it, if it is further away from what it's referring to, it's not likely to link. So if the subject is far from the verb, the recurrent neural network will suffer. Okay, so a good example is a book that a professor who won the award wrote is excellent, right? So the question is, what is excellent? Is it the book that is excellent, or is it the professor that is excellent, or is it the award that is excellent? So if you use a standard RNN or even LSTM or GRU based sequence model, you will struggle with this. Like if you ask it what is excellent, it will not know, because the book is actually what is excellent. It's not the professor that is excellent, and it's not the award that is excellent, it's the book. But the book is so far away from this in terms of the position with respect to the sequence that by the time your RNN-based encoder decoder sequence model is trying to decode excellence, it would have lost the meaning or the context that contains this book because you have compressed into a small context. So we already talked about attention. What was the whole idea? So the idea was let model focus on the relevant tokens, and that's it, right? Let the model figure out which tokens matter to this particular word. Okay. So the attention answer that question, which part of the input should I focus on right now? Instead of giving it a single vector, which was a context vector that the sequence model, LSTM and so on, based sequence models were doing, right? It will rather see all the tokens and compute the relevant scores between the tokens. Okay. So I think we've already said this already. So when you are translating this, the animal didn't cross the street because it was too tired. This it, is it the street or is it the animal, right? Who does so? But as a human being, you know which one it was referring to, right? You know, in fact, as you are saying the animal, your brain already has mapped that, okay, the animal is the thing, is the subject of this whole sentence, right? The animal didn't cross the street. We also know that street is the object. Even though the way humans understand it is different from the way LLMs understand it, humans have also a world model of it, right? A world view or a mental model of it, right? Not just a semantic um, contextual model or idea of it. So when you take the tokens that matter to this, to each word, you calculate the weighted sum, right? That gives you, and you sum it, that gives you attention. That's basically what attention is in terms of the mathematical formula or formulation of attention. And these weights are learned dynamically. The weights are learned as you're training the model. And remember, you're training the model sequence to sequence, okay? You give it an input sequence and it gives you an output. So, what is attention? This is kind of graphical, imagery that represents it. Um, you can see, um, so when you say the animal, right, you can see that this is kind of a representation of the attention metric. So each of the words here, the animal didn't cross the street because it was too tired, now has a way it kind of maps to this. The weight, that's the weight we are talking about. Now, in this case, we are just picking just one word. In this case, the it, which we are talking about. And you can see that these ones are lighter. That means the weighting is less, right? So the impact of this V is very small. But you can see the animal is much bolder, right? The animal is much bolder. And so you can see that it has learned, the weighting that it has learned has demonstrated that it is most influenced by animal. Then street also there's a little influence there you can see, right? But it's not as much as animal. Then the it, of course, this is what we call self-attention. How much is it influenced by its own self? That's it. These two tokens, which are basically the same thing. Okay. Then you have the period. So that is one. Then you have another one where you have this, in this case, street, you know, because it was too wide. Now, in this case, the animal didn't cross the street because it was too wide. So you can now see that in this case, it is a street that carries a greater weight, in terms of how it affects, um, you know, how it affects this. So simply because we changed this word to wide. Simply because we changed this word to wide. So so you can see that's basically a graphical way of viewing attention. So let's delve into it a bit more. Now, the other way you can look at attention is think of attention as a database lookup. So in the current modern formulation of attention, right? In the current modern formulation of attention, we have three, should I say, um, they're actually matrices, right? But let's say there are three vectors. Yeah, let's say there are three vectors. There are three vectors, right? You have the query vector, you have the key vector, and the value vector. And it is these three that are used to create this whole attention behavior and phenomenon. So, so this is how it works. While generating a word, right? The decoder is trying to generate a word. It is going to have these three vectors that have different meanings. The query is basically saying, what am I currently trying to translate? Or what am I currently trying to decode? In other words, what is the current decoder state? That's why it's called query. What am I looking for, right? That is it. What am I trying to decode or translate? The key refers to all the possible states in the encoder, basically. You can think of it as all the entire sequence, right? But in this case, it's not really sequence per se because it's now referring to the internal state of the model. And the reason why we're using this generic thing is because if you're talking about a sequence model, then we could say state. But if you're talking about transformer, right? Um, Rather, if you're talking about a sequence model, you could say sequence. But if you're talking about a transformer, then um, we will then say, okay, the output from an intermediate, part of the whole architecture, which we'll talk about. So, but anyway, the query is saying what is the current state of the decoder, or essentially what am I trying to predict next, right? Then the key is what are all the states in the encoder? In other words, what is the entire sequence from that is coming in from the encoder? That's another way of looking at it. Then the values would be what is, if essentially just think of values as what is my vocabulary, right? The decoder is asking, what is my vocabulary? How are each of the words represented, right? Or specifically the information that is available that I want to actually retrieve. The values hold a kind of think of it like a dictionary. Not I don't want to use the word dictionary. Think of it like a base, a database or whatever of the information I want to retrieve. So what the attention model is essentially doing is that it looks at the query and computes from all the possible encoder states or encoder from the entire sequence coming in from the encoder, which of them matters most? Which of the elements of the sequence matters most? Okay. And when it gets that, which of them matters most, it then calculates the computed sum, the weighted sum, like we've said, right? Does the softmax of it, and then uses that softmax to then select which of these representations um, it should send out. So remember, softmax is going to give you probability distribution. Okay. So the interesting thing is that the way this attention thing is formulated is basically um, a matrix multiplication, a matrix dot product, right? Then a scaling, then a softmax, right? Then another matrix dot product. And that is now the output. So that is differentiable. So we'll look at that shortly. So the simple thing is, yeah, queries are, you have three matrices are always given to you. Queries are basically, what am I looking for? Keys are basically, what is the things that are there, in the encoder? What does the encoder know, right? So when I take what am I looking for, a vector that represents what I'm looking for, and I do a dot product with a vector that represents what the encoder already knows, I'm going to get a vector of what are the important things that the encoder knows that I'm looking for. And then I'll now take that outcome. Only those important ones, I'll now pull them from the values. So the similarity score is Q dot Q QK transpose. This is a dot product, right? So um for each of them, the QK, I'm going to also give us some visual representation. But the higher score of this similarity score means a stronger relevance. So the one that has a higher score means that one has, that's basically this deeper blue, right? Deeper blue means animal is more important, then street is not so important, then so on, right? In this context, right? But in this other context, where we changed it from too tired to too white, the street, right? Um, the street now kind of had the highest relevance, followed by the animal, and so on. So that is relevance score. Then you normalize it, like I said, with softmax. The essence of normalizing is so that the sum of the elements in the softmax, each of the weights will sum to one, right? And then you take that softmax, right, and you multiply it by the values, the values, right, to now select which of the values matter most. That's the essence of the whole thing. So at the end of the day, the attention QKV is going to give you from this list of values, which values matter most. That's just what it does, right? In For each context. Okay, so it's going to give you a matrix that represents for each context, this is the values that matter most. So the question is, why are we doing a dot product? When the vectors grow large, the dot products can explode. So that's why you do scaling, okay? Um, it can become very large, so like exploding gradients and so on. Remember, a dot product is sum of the products, right? So if, for example, let me do a little bit of sketch here. So if, for example, you have this is normally how attention looks like, right? You have Q on one side and you have K on one side, right? And then um, think of this like a table, okay? Or a matrix of Qs and Ks, okay? And then you're going to have values in. So let's assume that each of these Q, right? Each of these slot represents a piece of the token. So like going by that example, um, what was that example? The animal was too tired, right? Because the animal didn't cross the street because it was too tired, okay? So let's say we'll go with that. So we will have something like this is D, right? This token is D. This is animal. This is did not did did not cross the street. Something like that. Okay. And then you also have the same thing down here. You have still the right animal did not right did not cross. So it keeps going that way, right? And this also keeps going this way. Now, in this matrix, that means you have the query is like a list of vectors that says for each of the key. So in a self-attention mechanism, which we are starting with a simple implementation, what we are saying is that for each word, it also has a value of its importance with respect to other words. So how important is it with respect to itself? You give a number, maybe like 0.1, right? Then this same how important is it to this next word, which is animal, right? And it could be maybe 0.2, right? By the way, this whole thing is this is a learned parameter. These are all learned parameters. As you're training the model, it's learning all of those things. Then did will be 0.1 and so on, right? So then animal too, okay? This animal, the relevance of D to animal will also be here. The relevance of animal to itself will also be there, and so on, right? So you just keep having values in this. That's basically what we mean when we say the attention matrix, right? It's basically saying this will all have numbers, and the larger number. So if you had a very large number here, maybe like 0.8, okay, it means that animal did matters is a word that matters most, to the meaning of animal in this context, and so on. So it's always going to be a matrix, and that's the Q and K. Because effectively, in the context of a sequence, right, you can just take the K to be the input. Remember, Q is what am I looking for? K is what do I already know? So with respect to what I'm looking for, but in actual usage in transformers, you find that these are not actually these words as they are. There are other things, right? There are vectors too. But for the sake of explanation, we can use the words. Okay, so that's what we mean when we say the attention matrix. We basically are saying the vector dimension. So if the vector dimension is 1024, that means that you have 1024 rows by 1024 columns. That is the attention Q and K matrix, right? So if you were to calculate dot products between those QK, you'd see that you have very large values. And these large values will automatically lead to what? Exploding gradients. Because remember, whenever you have large weights or large um, you know, costs or large gradients, yeah, you have exploding gradients basically. So in order to avoid exploding or vanishing gradients, right? What we would now do is scale this by the square root of dk. And if you ask me why did they choose square roots, I will not really say. I think it was more as a result of research, right? Because you could have said, let me just use the key dimension, right? But then the key dimension is basically the number of um the size of the key vector, which is also the same as the size of the query vector because they're always the same size, right? The key vector is always 1024. The query vector is always also 1024. So when you square them, you now have a square, which is dk squared. Well, dk squared. So if I took a square, it should be dk, right? But I guess it's because of the effect. We now use a square root. So this is something I'm always asking, how did they arrive at square root? But that's what we have. It's a square root, right? And and that's basically how this was arrived at. So by the time I take the Q values, which will be how each of the Qs attend to each of the Ks, and multiply by the K has to be transposed because remember, let's assume you have um remember that each of these Q and K you may have multiple of them. If you have a multi-head attention, there's something we call multi-head attention, right? Or if each of the embeddings in that attention thing, each of the words have embedding. So what's actually happening is that remember in the other page I showed you a table that had words. Now, those are just single words, but those words represent embeddings. So each word has an embedding vector as well as the key dimension. So it has the embedding dimension. So let's assume your embedding vector is maybe 128, 128, right? Then you have an embedding of 128. Then let's assume that the key dimension itself, that is the key sequence, is 1024, right? So you're going to end up with Q being it's going to be 128, right? By 1024. That's the dimension. Okay. That's the shape rather of Q. And then K, which is the keys. The keys basically remember the Q is query, what am I looking for? While key is what is there. right? What are the words? The entire vocabulary basically. Now, K is also the same shape as Q. So K is also 128. Q and K are always the same shape, right? So K is also 128 by 1024. Okay, so for you to do a dot product, remember I said that dot product, the middle dimension has to be the same. So for us to do a dot product, right, Q, if we have Q to be 128, right, by 1024, right, and K to be 128 by 1024 as well, then the Q, you have to transpose the K. So K transpose, right? K transpose, let me just use K dot T. K transpose is going to be transpose dimension, which is 124 by 1024 by 128, right? So when you now do Q dot, K transpose, okay? What you're basically doing is a dot product of 128 by 1024, right? Dot 1024 by 128. That is what that will give you. So the result of um this matrix dot product is now going to be basically, so it's going to be basically the shape. These are all shapes, so not actual values, by the way, which is a QK, right? QK transpose. The shape will now be 128 by 128. So this is just going to give us um how they all attend to each other. Okay. Again, remember 128 is the embedding size, while 1024 is the number of you know um elements in that in the vocabulary basically, right? And that's it. So when you now do this QKT, you now have a shape of 128 by 128. You now do a soft max, it's still going to give you 128 by 28, 128. And then you can scale it. You scale it first, and then you do soft max. The scaling is this divided by square root of dk, and then you do a soft max. And then after you do a soft max, you now multiply by v, right? So this is now Q dot K transpose, right? Okay, after you've done the soft max doesn't change the shape, so the shape is still the same. Scaling doesn't also change the shape, so the shape is also going to be the same. This is square root of dk, right? Then when you now do dot product with v, so this is what you are getting. It's still the same shape. All of these other are basically scalar operations, element-wise scalar operations. So you are just going to have 128 by 128, right? That you now dot it with v. V is 128 by 1024. So V is still the same shape as Q and K. That's one thing to understand. They're all the same shape. Q is 128, QKV, they're all the same shape. So this will now give you a shape of because it has the same middle um dimension, you now end up with 128 by 1024, which is basically giving you back the original is basically giving you the same shape as V, but except that this time around it is V as has been. The ones that matter are the ones that are selected. The ones that don't matter will have low value. So this is just using shapes to kind of show you that this is a valid operation. Okay, so the main thing with the scaling is that it prevents unstable gradients, makes gradients really small, and then it enables us to make transformers that have more layers. Okay, so that is attention. Now, there is something called self-attention. We started off with attention, right? But self-attention became like a breakthrough. So before we had transformers, we had attention that was used between encoder and decoder, like I've said, right? So the output from the encoder, in this case, the encoder being the LSTM encoder and the decoder being the LSTM decoder. So you would have the attention in between the two of them, right? To allow the decoder to figure out which of the sequences from the encoder matters the most to what it is trying to predict, right? But afterwards, the attention is all we need paper basically came up and said, you don't even need that. Let each token just um, attend to every other token in the same sequence. Instead of taking tokens from the encoder and to see how the tokens from the encoder affects the tokens generated by the decoder, which is what we had before, right? And that's what we're talking about when we're talking about QKV and so on. Okay. Um, So, but with transformers, it was just self-attention. Let's see how train on a token against itself, right? Train a sequence against itself, do an attention setup, of a sequence against itself, and let the sequence, let each of the tokens in the sequence, let's figure out how they, um, affect each other, right? And that's pretty much what I have been showing you here. Basically, how attention is now, which is the self-attention, versus what was before, which was encoder decoder attention, right? Using the attention to basically um, associate the sequence in the encoder to the sequence in the decoder, right? And it just came up with really interesting stuff, right? Um, so one is with self-attention, right? You could figure out, you know, um, so let's look at it this way. Self-attention allows your tokens to look at each other and weigh the importance of all the other tokens, right? In a sequence to grasp the context. So you use one set of projections. So when we say projection, the projections are QKV. I'll explain what projections are, but basically think of projection as whatever is the input that's coming in, I project it onto a specific, dimension, right? So for example, you could say you want to project it onto a 128 by 1024 dimension, where the 128 represents the embedding size, like I've said. Okay. So the three QKVs are projected into the same, onto the same, basically same set, right? So self attention now says, okay, for each word or each token, how much does it influence the other, right? So what we've been talking about really has been mostly self attention. We have what we call multi-head attention, which is self-attention, but across multiple, you split it. So, I think I'll better explain it with some of the sketches I have, just in a few slides down when we're talking about transformers. But basically, multi-head attention says you have multiple heads or multiple implementations of self-attention. Just think of it that way. Parallel self-attention, um, but each of the weights are slightly different. So you learn a different set. The projection itself, what generates this projection, the weights are different because they're learning different things. So just think about it the way when we're talking about convolutional neural networks, when we say that each filter, right, is generating a different set of features, considering a different set of things. So in the same way, each head in a multi-head attention is still an attention, um, you know, mapping or table, but it is trained to essentially um, do a different kind of, relationship, between the tokens, right? So that's what multi-head attention is. And what it does is that it allows the model to capture simultaneous different relationships and perspectives, right? Which can then be combined. So And why why self-attention, multi-head attention matters is that because of this, the fact that first of all, you have the scaling to reduce the vanishing gradients and exploding gradients, and the fact that you have each token attending to every other token, right? Then you end up being able to capture long-range dependencies. It is no more a matter of how far away, because they are basically in the same matrix, right? So it's no more a matter of how far away is this word from the other word, because in the same matrix, it doesn't really matter, right? That's the first thing. The second thing is that it allows the full parallelization. I don't have to train on one token at a time. All those tokens come in at the same time. We'll look at that more when we're talking about the transformer model. There's no recurrence and there's no convolution, right? These are things that tend to slow down training. The LSTM was removed because there's no recurrency, right? Um, there's no recurrent network. There's no recurrence in the network. And then there's no convolution where, convolution is like, we talked about convolution already, right? Which is you're still calculating the average from a particular spatial area, right? So we're not doing any of. So transformers are really fast because it's not doing any of those slow stuff. Okay, so this is kind of what I was trying to explain, that when you're talking about a self-attention matrix, if you look at this, right, you have the animal didn't cross the street because he was too tired. That's the keys, okay? Then you have the queries. Also, the animal didn't cross the street because it was too tired. So this is self-attention. This is basically saying, how is each word attending to itself and to other words, right? So this matrix gives you like this is how D attends to animal, right? The value is 0.4. How it attends to digit 0.02, and so on, all the way to the end. So you can already see that it really attends to animal the most. Okay. And then you even see where the one that matters was it in this context rather, it really attends most to animal. Okay. It also attends a bit more to tired because of course it is what is tired. But you see, so these values again are learned values. We're not hard coding this. As you are training the model, the attention matrix is a parameter um, matrix, basically. So it is learning. The parameters are getting updated. It is being trained. It is learning. And as it is learning, these parameters are adjusting to come up with the values that give you the best, um, you know, linkage or attention between the different words. So this is self-attention. And this is basically the calculation. Like I say, it's a matrix. The input matrix. So what happens is with attention, you have an input matrix, right? The the X is just like it's the X we normally use to represent any input. Okay. And X is a real number, right? That's what this thing means. It's an element of a real number set. This R means so X is a real number. In other words, it's a floating point number basically. Well, it could be a complex number as well because complex numbers are real numbers, but it's a real number. But the most important aspect of it is that the dimension of X is n by d, where n, right, is d is you have the dimension of the embedding size, right? And then the number of basically the number of elements, right? So X is an input. So you now project this X, and this is what we mean by projection. You apply some weights. So these weights are learned weights, okay? The WQ, the model will be learning it as you are training it. The WK as well, right? And the WV. So these are all weights, which the model is basically learning how to project this X into um, a vector, basically. Well, it's not really a vector, it's actually a matrix, right? That is made up of embedding by the the attention depth or attention, yeah, we can call it attention depth. Embedding size by attention depth. So each of them will be projected into the same dimensions, right? But the actual values that come out will be different because the weights are different. Okay, so that's um so same thing with the V, which is the values. Okay, so this is how you get QKV from the input. In case you were asking, we've been talking about QKV. So, but where does this QKVs come from? The QKV is basically projections, and the projection um the when we say projection, so think of it like when we're talking about embeddings, we're saying that if you learn an embedding, you are basically learning um a meaning, right, to the words or whatever input you pass in, right? And you learn in such a way that the meanings have there's some kind of meaningfulness, right? There's some kind of correlation between things that mean the same thing, right? The embeddings kind of have the same thing. They're similar rather for things that have similar meanings. So in the same way, projection is also a learned, these weights learn a kind of linear transformation, right? And this linear transformation, like you can see, you basically multiply these weights by the X input, and it would it will map the input embeddings, which is X. Like I said, the X is n by the D, which is the embedding depth or embedding dimension, right? This will now map it into three different subspaces. So the Q, the K, and the V, right? And so the Q will come out length because the weight is length. The X is the input, so X is a signal that comes in. But the WQ, WK, WV are the weights. So with this, you get a QKV, and we've already talked about how you get the attention from the QKV. You do the Q, transpose the K, you multiply dot products with the Q. You scale it by the DK, which is the depth, right, of those vectors. And then you softmax it, you multiply by V, right? So what this means effectively is that um, projection is like, think of projection as a feature extraction, just a feature extraction, basically. So a feature extraction from this, but this feature extraction, this weight determines the features that are extracted from this Q, from this X rather, and they're called Q. And those features then determine like how this Q attends to K. In other words, how this Q will select among the K, which is also another projection, the ones that matter most. And then when all of that is done, you now multiply by V. V is giving you the value. So it's an interesting thing. And I think it's something to keep thinking about until you master the concepts. So implementing scaled up product attention is actually very simple, right? This is how you would do it. Basically, a decay is Q size, the size of Q, the last dimension of Q, which is the embedding dimension, basically, right? And sorry, not the embedding dimension, the depth, the attention depth. So in that case, example where I was saying 128 by 1024, DK will actually be 1024. Okay. Then you do the calculation. So this is just a calculation of it. K transpose, you transpose -2, -1. Basically, you transpose the last two dimensions. You transpose the embedding dimension and the attention depth, right? You transpose those two and then you multiply by Q, right? Then you divide it by the square root of the depth, which is dk. That gives you all the scores. And then weights, right? You run softmax on the scores, okay? And then after that, you multiply again a matrix multiplication, which is a dot product multiplication between these weights, which is the scaled version of it. You multiply by the value, and that gives you the output. That's scaled thing. So typically, this is the shape for your information. If you're asking, okay, why am I doing all of this? This is typically the shape, right? But this is for a multi-head attention. If it's a single head attention, this head will be one. The sequence length, again, remember, is the sequence length, which is the number of words that your a transformer model wants to handle, or whatever that attention wants to handle. That's the sequence length. And then decay, which is the depth of the attention. Okay, so we have two types for encoders. For decoders, we have what we call masked self attention, right? Um, so let's see. The best way to explain this is this. For encoders, we will have this full thing, but for decoders, this section, right? We don't want this section. Let me write it so we can. So for decoders, right? The main thing with decoders is that because the decoder is decoding, you don't want to show it the you don't want to show it the rest of the sequence. You don't want to show, because if you show, I don't want to show the, let's say that the decoder is at THE and it's trying to predict the next word. So at THE, I don't want to show it the rest of the sentence. Okay. So that means everything that has to do with this, I will remove it. I don't want it to see or know. So I'll remove it, right? That's basically what masking means. Okay, so when I am, in fact, let me use a color that totally mask it, right? So when I am at THE, right, this number is telling me how much it attends to the previous, like Sorry, we had a slight outage. So I was trying to explain the um when we say projection, what we mean by projection, and uh, okay, so I was trying to explain what we mean by masked self-attention. So when we say masked self-attention, right, we actually have in the encoder, you are going to give the encoder everything, right? You give it the as you are training it, right? You are giving it all the input sequence, okay? But the decoder, when you are training the decoder, you're not going to give the decoder the next word. So think about it this way. I in a transformer architecture, right? I have this sequence, and so I have a sequence, right? Typically, when you are training encoder, you are going to give it. Let me uh, kind of see if I can simulate this with my um, Excali draw. Okay, so remember we have a table. So just think about this as the table. Think about this as a table, and so the table I just showed before, where you have the rows and columns, right? Now, typically you are going to have a sequence of words. So, for example, the animal did not cross the oh, sorry. Okay. Right. So I was the animal did not cross the road because it was too tired. Okay. Um, right. So then you also have similar things here. The animal did not cross the road. So basically something like this. Okay. Now for the encoder, when I'm training, I'm going to give it this entire sequence to train on, right? Because you are passing in this sequence into the encoder. But for the decoder, because I want the decoder to learn. I'm not going to tell the decoder the next words. Okay. So when I want the decoder, when I am on THE, I want the decoder to be able to guess the next word, right? Um, so I want the decoder to be able to guess the next word. So I only give it the words that it has already guessed so far, right? So I'll give it THE. So when I'm at THE, I'm only going to give it THE. I'm not going to give it the entire sequence, because if I do that, then um, I am kind of, you know, let's just say, yeah, think of it like, okay, we are giving the decoder expo, right? Which is not, you want it to be able to, you want to train it to predict. So you should not give it the information you want it to predict, right? Rather, you give it the previous sequence, and then um, you give it what it is supposed to predict. Okay. So that is what, so on the decoder side, what that means basically is, let's go back to this. What that means is you will not, in this attention matrix, if I allow everything to show, then this side of it, which is the future, the incoming, sequences, it will also know. So it's not actually, we're not, um, it's not learning to predict basically. So what we normally will do is we will mask this future. So when I'm at THE, we will mask everything after THE, which is animal didn't cross the street because it was too hard. When I'm at animal, I'll mask everything after animal, which is didn't cross the street, like that. When I'm at didn't, I'll mask everything after didn't, right? So what masking in this case means is that you are going to give the weight a zero value so that the attention calculation will not take into consideration the future tokens, the tokens that have not yet been generated, right? So that's what we mean by a masked attention, layer, or a masked attention. It basically means that these values on this side of the matrix that are showing how these words attend to future not yet reached words, right? We will give it zero so that we don't skew what comes out of the attention matrix. So that's just what I want to explain in that regard. Okay, so let's move on. So that's what mask self-attention means. Because when you are generating text, you don't want the model to see the future, because if not, you are cheating, right? You are telling the model the answer instead of allowing it to learn to generate the correct thing. So what we normally do is the same thing you saw me do there, which is basically this, right? We'll basically just everything on this diagonal matrix, from this diagonal matrix up, we will give it a zero value. So effectively, what that zero value does is that it masks it, right? So that when you are doing your attention dot product, everything in the future is not going to be included. So that's it. If not, predict the next word. The attention um, matrix or mechanism or the model itself will always get the correct answer, because you have in a way given it an idea of what the future, is. So that's the whole essence of masking. So you zero out the future attention scores so that you now have what we call a triangular matrix, that at the bottom, right, you have the values. These values are not always going to be one, right? Like I showed you in the other one. So this results in what we call autoregressive generation. So autoregressive generation is a kind of generation where you are training the model, and then the model generates the next word, like what we did before. When it generates the next word, then that next word becomes part of the sequence it uses to generate the next word. and so on and so forth. Okay, so so this is example of a mask attention. So remember, we just did attention without masking. It's basically the same thing. The only difference is that we will create a mask fill. So the mask fill is achieved by creating a triangular matrix. So the touch.tree is going to give you a triangular matrix, but it's going to start off, it basically it's a triangular um, truncation, right? So you first of all start with a regular matrix that of sequence length by sequence length, right? So remember that's the dimension of your attention, the maximum sequence length you want to give. So that will be the dimension on the on the attention table basically. The dimension of the attention table is always sequence length by sequence length, right? So what I was calling the depth, right, of the attention. So sequence length here, right? That's the width, right? And then you also have sequence length as the height as well. So that is the dimension of that table. And based on that, um, so based on that, now that's what touch.ones will give us a matrix of ones, only ones in it. Then the touch.tree will now trim off by the diagonal. So you specify the diagonal. Diagonal equals 1. So it's going to trim off at diagonal 1. So diagonal 1 is this first main diagonal, right? So it's basically going to trim off at that diagonal, the upper side. So that's what tree means. Tree means triangular upper. So it's going to trim off the upper side, this upper side of the triangle, basically, of the matrix. And those ones will be zeros, while everything on this side will be one. Then you convert them to Boolean, right? And that makes a mask. So you now use the mask fill, which is this function, basically, to fill anywhere that you have one, you fill anywhere you have one, you fill minus inf. So minus inf is negative infinity. Then so anyone that is in this mask. So first of all, you are doing an um upper triangular matrix. That's what tree means. So this upper side, you fill it with values of 1, right? Then you convert it to Boolean, right? So so everything up here will be true, while everything down here will be false. That's what this part of the code does. Then you now do masked fill. So mask fill means any part of this mask that is true, you fill it with this value, right? And any part of this mask that is false, right? You will not fill it with any value. You skip it. That's what mask fill is. So this bottom side is false, remember, while this upper side is true because we use a triangular upper matrix with diagonal 1 and we filled it with ones. So everything here is true. So everything up here will be filled with the minus infinity that we have here. I'm just going to use lines to draw it. So yes, so we fill this entire side with minus infinity. So what happens is minus infinity is a very low value, while up here is the ones is whatever value was in the scores matrix, right? So when you now come and do a softmax, so remember softmax will rescale everything, right? So everything adds up to 1, okay? So we're going to basically do a softmax. So when you rescale everything to add up to 1, anything that is minus infinity will basically go to 0, right? Very small because it's negatives, very negative values. Very negative values always go to 0 in a softmax. And then positive values become very high. So that means every value here will be high and they will all be the same or whatever they weigh, they will all add up to 1 anyway. While the values here will be 0. So this is basically the method that is used to generate the masking of the upper triangle of the attention map or the attention matrix, which you will now use those weight metrics. Remember, this weight metric is gotten from the standard matrix multiplication of Q and K transpose, right, divided by dk, square root of dk, which is dk raised to power 0.5. So you get the scores, right? And then all of this is basically for you to calculate a mask, right? And then here you apply the mask to the score. Here you use soft marks. So at the end of the day, remember, you still have to do soft marks. So, but by applying negative infinite value, anything above here becomes 0. That's what soft marks would do. And then you apply those weights to V, which is the attention times V. So that's how you implement the mask, attention, right, which is needed on the decoder side. Okay. So let's talk a little bit about multi-head attention, and I think we will just end it at this point. So the multi-head attention, you have a situation where a single head of attention is this. This is everything we just talked about, right? You have the QK, you have a dot product matrix multiplication, you have the scaling, which is divided by square root of dk. Then you have the mask. The mask is optional. You only use the mask for decoders, but for encoders, you don't use it. That's why it's optional. Then it goes to the soft marks, and then this is another matrix multiplication of that result by the V projection, right? And that gives you, this output is the attention. That is what is called the scale dot product attention. That's the outcome of a single attention operation. Now, but this single attention thing just basically gives you one way by which different tokens will attend to each other and to themselves, right? But there may be many other ways, right? Depending on the context. So in order to implement those many other ways, we now use what we call multi-head attention, where we now take this single attention, right? That we have done here. Okay, we take this single attention and we basically multiply it, right? We take this single attention and we replicate it. We make copies of it, right? So you make multiple copies of it, right? And these multiple copies is what you see here, right? Because this single block represents this entire thing, right? This entire scaled up product attention. But when we now take this, we multiply it across the same way we were using multiple filters or multiple filters in convolutional neural networks. We now have multiple heads or multiple attention heads, right? In this. So each of these attention head is now able to come up with a different way that the words or the tokens attend to each other, basically. So you end up coming up with different ways. And the basic, the advantage of using multi-head attention is there are different ways of looking at the relationships between the words, how the words attend to each other, rather than just using only one way, which would be equivalent, for example, in a convolutional neural network of using just a single filter, meaning you are only extracting a single type of feature or feature set. But with this, you are extracting multiple types. So that's where the multi-head attention comes. And the H is just telling you the number of heads. In other words, think of it as the number of filters in CNN, but the number of heads, which basically represents the number of different ways that words can attend to each other. So the thing you will now see is that maybe one head can learn syntactic relationships between words, right? Another head can learn semantic relationship between words. Another head can learn the positional relationship between words. Another head can learn maybe meanings and opposites and synonyms and so many things. So you now give the model the ability to learn different kinds of things. That's the benefit of using multiple heads instead of one single attention. We run several in parallel. And that's basically what a multi-head attention is. Just basically a single attention, right? But run in parallel. So the way it's normally done is that you would now have each head, and then the heads will each have its own attention mechanism, and then those heads will now be concatenated. When they have each of these outputs from the multiple heads will now be concatenated. Concatenate basically means stack them again together, right? Remember, each head is going to give us something like 128, like I just showed you before, 128 by 1024 matrix, right? Or any number you like, right? Where 128 is the embedding dimension, while 1024 is a sequence length, right? Which is basically the attention depth, right? So um, this can learn one. So if you have multiple heads, then you could have five of these, right? So you are going to have, when you concatenate them, it will now be 128 times 5, which is um, 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 640 or so, right? So yeah, so that will give you 640 by 1024. So typically what they do with multi-head attention is you first of all divide this by the number of heads you want to have, and then you do multiple heads. Then when you have done all the heads, each of the heads, you now concatenate it back. So you always get the same embedding size at the end of the day, right? So yeah, that's just a summary of what multi-head attention is and what it does and the benefit over just having a single head or a single scale dot product attention. So this is code for multi-head attention. Actually, in Touch, there is a built-in function, so you don't even need to manually do it yourself. You just call nn.multi-head attention. You specify the embedding dimension. So that's the first dimension. I was saying it's 128, but here is 512, right? Then the number of heads you want to have, then batch first, right? And that's it. So here you can now see we have batch 30, sequence length 20. This is embedding 512, right? And so when you do attention, you run MHA on this. I'll do some of these examples when we do hands-on next week, right? Um, yeah, but then you will see output with MHA XXX. So essentially, we have created three different sets of data. We now pass them into the multi-head attention, and we get three sets of things. So what's happening internally in a multi-head attention, like we saw, is that you first of all have the linear projection, which is a QKV linear projection. Then the QKV will have a dimension of 5112 by whatever sequence length it is, right? And then it will be split into heads. So these 512 embedded dimensions can be split into 8 heads. So each head will have a depth of or a depth or it will have a depth of 512 over 8, right? Which I think should be either 64 or so. Yes, it should be 64. So you now have each head has an embedding depth. I don't call it embedding anymore. In this case, you just call it a depth of 64. So you now have 32 by 20 by 64. So sequence length is still 20, which is the size of the sequence or the size of the attention matrix. So that's the splitting into heads. Then you do the parallel attention. So like in this case, you do parallel attention across the 8, right? And then after you concatenate. So remember, let me write some annotation here so we can really understand this. So first of all, the linear projection that's coming in, the X value is 32, 20, 512, right? That's what's coming in. Okay. Then you split it into heads. So we've already specified that there are 8 heads here, right? So when you split into heads, you're going to have 8 heads. Now, typically, the way we write it is 32 is still the batch size, right? So since batch first, we always keep 32 at the first. Then we'll have the number of heads, which is 8. Um, and then the sequence length is still 20. And then each head is 64, right? So you now have 4 dimensions, right? But the main thing is that you now have 64 depth of each by um, by 8 heads, right? The sequence length is still 20. Then you do the parallel attention. So the parallel attention is actually basically doing attention on 32 by 20 by 64, right? But you are doing it 8 times in parallel, okay? Then when you have finished the attention, you still get the same dimension out because the V is always the same, right? The V is always the same. Then when you are done with that, um, you will now do concatenate. So concatenate is where you join back the 8 heads into one single head. So you are concatenating, it's going to go back to 32 by 20 by 5112. So you join back the 864 depth heads, right? And then that will be your final projection. So the final projection is going to basically be that 32 by 20 by 5112. If you want to do anything else with it, maybe pass it through what do you call it? A linear layer or something, you do that. So this multi-head attention is very, very critical. It is really one of the most important aspects of um, machine learning, deep learning, especially for models, right? So it's one of the most important. Okay, so so that's the code for multi-head attention. I'm going to stop here, right? Because we have kind of gone past our time. Um, when we come, we will talk about transformers, right? But let me just give you a quick preview of, um, you know, so transformers use attention mechanism. When we come back, I want us to just try the attention mechanism alone first before we talk about transformers. But what are transformers? Transformers are basically a kind of neural network architecture that use um that use basically attention and nothing else. And that's why, like I said before, there's a paper that was written by a group of Google researchers, a Google Brain AI researchers, and they came up with the title of the paper is Attention is All You Need. And that's because they basically before this paper, we used to use attention in between the encoder and decoder in recurrent neural networks and even in convolutional neural networks, right? So they just came and they said, well, you don't really need RNNs anymore. Just take attention, take the RNNs out and use just attention. But you build some stuff around it, the projection. So you see the projections we just talked about and so on. So that's why they came up with that name. So we are going to talk about that and we're going to look at the architecture, right, of it's still made up of encoder and decoder, right? Even though there are transformers that are only encoder, right? And there are even transformers that are only decoder, but it's still the same sequence model, still encoder decoder output. But you can see this is the architecture of encoder and decoder, and we're going to talk in detail about what each of these are, right? Where you see the self-attention we just talked about, which is basically this projection, QKV, and all of this Matmos scale, mask, softmax. And, you know, same thing with decoder. So we are going to talk about this and then we'll go to implementation. But yeah, that's a preview. But just remember that even if you don't really understand all of what I went through, right? But just remember that attention is like one of the most important elements in language, natural language processing these days, right? It was a game changer, right? But the real game changer was when they used attention and removed those sequence models and we came up with a transform architecture. Why that changed the game was speed of training and speed of inference. It is incomparable between sequence models and transformers. Transformers are like 100 times faster to train, right? So because they're 100 times faster, they can do bulk work, more of, you can train them on more data, you can add in more layers and so on. So we'll talk about that when we meet. Thank you, everyone, and let's have a good evening.